In this video, we are going to talk about how lasers work and possibly how to build one. I'm not an expert for lasers, so I had a call with Zach. I recorded this call and that's what you will see in this video. So let's start. Here is my call with Zach. Can you really build a laser at home?
Um, I mean, in theory, you could if you can get all the materials. The issue is that the materials are kind of exotic. However, you could get like a laser diode and you could build all the electronics around it.
A
And so you
small
could,
diode or also big one?
no, you could actually buy commercially relatively high power diodes. And then you could build all of the stuff around it and build your own enclosure. And now you have a laser.
Okay, so and why we would like to build a laser?
Ah, yes. So there's all sorts of reasons, right? Um, so I mean, you're like kind of bare bones practical is shown on this screen where you have, a laser pointer, right? So it's an indicator. Laser light shows, those are obviously fun, but there's practical uses too. So I'm sure you've heard of LiDAR. So LiDAR does use lasers.
Oh, I didn't know that. So these are the sensors used, for example, in cars.
Yeah, so LiDAR is used for range finding, but you can also use it for imaging.
Mm-hmm.
And compared to so one of the things is that ADAS sensors are doing now with radar is they want to do 4D radar imaging. Okay, so essentially you build a 3D scene with a radar beam, and then it evolves in time, and then you can essentially stream that data and you have a radar driven image or video. I guess you could say it's a radar driven video. But you can do the same thing with LiDAR. Just with LiDAR, you get much higher accuracy.
So LiDAR, it means L is the laser or light.
Well, L means light, but
Okay,
you're doing it with a laser. Yeah.
okay.
Yeah. So your laser is your light source. And like I said, you can buy commercially just, little diodes that have that can get to pretty high power output. And you can just buy them from distributors.
Mm-hmm.
So I think Hamamatsu makes a good one. Hamamatsu makes a lot of electro-optical products. I think they're one of the leaders in that space. I believe. Don't quote me on that.
Are not
But
these?
go.
Yeah, go
Oh,
ahead.
go ahead.
Uh,
I was going to say go to Octopart, go to DigiKey, go to RP Photonics, just search for high power laser diode, and you'll be able to get the actual diode. Now they're not going to give you like the driving circuit and all the control stuff and everything around it, but you'll get the actual laser diode.
okay. So now I have two questions. I have to write in note. So first one, are not these lasers like dangerous?
Well, sure, they can be, and actually lasers are rated using a class system. So it's the uh, level of danger created by a laser is classified based on the maximum permissible exposure that your eye can receive, either from a direct hit or from diffuse reflection. So,
Mm-hmm.
like reflection off of a surface. And that's how they're classified. So, your typical like laser pointer is they tell you not to point it at your eye because long-term exposure can do eye damage, but brief exposures, these are 5 milliwatt lasers, they're not going to be damaging.
Okay. And you can buy also diodes which can be dangerous.
They can be dangerous, yeah. In
Okay.
fact, I don't know if you've ever watched any of the Hacksmiths videos, but they actually build a laser. But as I recall, they actually got a really high power laser, and it was definitely something that could be damaging to the eyes.
Yeah. And I've seen some videos about lasers pointing up to the sky, and I think people should not do that.
Absolutely not. Yeah, because those beams they diverge, and so they expand. Like here on the image with the laser pointer, it's a small beam that comes out, but over long distances, it actually expands, and it gets to a very big spot. And so that spot can then interfere with the vision of the pilot. And yeah, you obviously don't want a pilot to have their vision interfered with, and when they're trying to fly a helicopter or a plane or something.
Where else lasers can be used? Shop, some effects and pointers and
Yeah,
CD-ROMs.
yeah, CD-ROM. Yeah, if anybody still has one of those, do they even make those anymore?
I don't know.
They don't even make CD burners anymore. But CD burners, if you remember those,
Yeah, I do.
you and I are of an age where I'm sure we both had CD burners. Let's see what else. In industry, so precision cutting, so laser cutting, laser drilling, obviously in PCBs. Um,
How
they
they
are
can drill specific depth, for example, by laser? Do you know? When they do micro vias, for example, in PCB.
Yes, I can. So I don't have that in this presentation, but I will actually. There's a slide where I can kind of explain a little bit of that. So
Do they use
yes,
like reflection from the copper or?
no, no. What they're actually doing is that it's based on the focusing depth.
Oh, so you can focus laser into specific depth, and then it's not going to drill deeper.
It. What will happen is the power level will only be really high within that certain range. So that's done by selecting the right lens. There's different types of lasers, okay? But this all relies on something called stimulated emission. So that's the S and the E in laser. So basically, what's happening is before there's any light emission, okay, I send in a photon, so just one unit of light, and it excites an electron into a higher energy level. So if you remember anything from like a chemistry class, you know that all the electrons are organized into different regions around the nucleus in an atom, and they all have a different energy. So you give an electron some energy, and you're basically putting in, out of phase light, just random photons. Okay. Then eventually one of those will decay and go back down to a lower level. And so it emits a specific wavelength of light.
Is it
But
same
then,
wavelength as the incident photon?
no, it's based on this,
Energy between the two.
yeah,
Okay.
this energy difference. Yeah. So the energy difference tells you how much energy that photon has coming out. So that photon can come over here to a nearby electron and then cause it to then also emit.
Mm-hmm.
And so by doing that, you basically get two photons that are lined up in phase. And so if anyone's listening and understands about like RF design, you know that every wave has a phase associated with it. And if two waves have the same phase, they line up in time, and then their intensities can build up to very high value. And so that's how you're getting the one wavelength at high intensity, is you basically have all these photons that are being emitted in phase from different parts of the material, and they all essentially add together to give you a very high intensity pulse of light.
Mm-hmm. And this can be done in different kind of environment, correct? It can be done with, I don't know, some materials or air or I don't know.
Oh yeah, so there are all different types of materials, all three phases, solid, liquid, and gas
Mm-hmm.
materials. We'll do this very easily.
So you can have
Theoretic,
liquid laser.
yes, yeah, and I'll explain what. Yes, there are liquids that you use for lasers. They're called dye lasers. But theoretically, any material could exhibit this effect. It's just that in many cases, the amount of light that you need to cause this and have it be noticeable is so much that it actually damages the material. So you basically destroy the material before you ever see
Mm-hmm.
stimulated emission. But
But when
some
you stimulate it, you
materials,
can stimulate it also with electricity, no? Do you need to stimulate it with?
exactly, yeah. So with a diode laser, like a semiconductor laser, instead of sending in this incident photon to send an electron up to a higher energy level, I just use electricity.
Okay, so let's move to the next page. What do you have here?
So just kind of the backtrack, like, when we say like laser light, remember, like, you actually have like a wavelength and a frequency associated with the light. And a lot of lasers that everybody, I think, focuses on are, they look in like the visible spectrum. And, really they can be anywhere in the visible spectrum, but what determines that is the material.
Mm-hmm.
Okay, so the type of material and the the atomic characteristics, basically how the electrons are arranged around the material, the atoms in the material, basically tell you what possible wavelengths you can have and emit as laser light.
Is there difference in power between these colors or frequencies?
Is there a difference in power?
Yeah, I mean, like, does it mean like blue laser is going to be always more powerful than the red one?
I see what you're asking. Yeah. So, I mean, not necessarily. There's a lot of other factors that go into getting to high power. I mean, it's true that like a blue photon, because it's at higher frequency, carries higher energy than a red photon. But that doesn't necessarily mean a blue laser is always going to be more powerful than a red laser.
Mm-hmm. Because I
And
guess, I mean, it depends on the input power, of course, but if you have like same power input, if they will have different uh, output.
yeah, yeah, I see what you're asking. And again, it you can't really make that one-to-one comparison
Okay,
because the material that gets you the red laser is going to be different from the material that gets you the blue laser.
okay,
And then
okay.
also like there are infrared lasers. So, to the right end of this red portion. And then there are deeper ultraviolet lasers. So one of the lasers that I used all the time was a neodymium YAG laser. So it's a specific type of crystal, but it operated at 355. So it's pretty deep into the violet region.
How do you
So
decide which
355
color you
nanometer.
would like to use?
So it just depends what you need to do. So it depends on the application you want. Like for your laser pointer, right? You would want to use red or green because that's lowest power and the human eye is going to be most sensitive in that region. So you have low power laser output. But let's say you want to do something with like with probing. Uh, okay, so like very fast lasers can be used to probe like charge carrier dynamics in semiconductors. So this can be for scientific studies,
Okay.
can also be for testing. Um, just as an example, some of those fast lasers, it's going to be easier to drill with certain colors because the material that you're drilling is going to be more absorptive
Mm-hmm.
at certain colors. So you would choose the color based on the application.
So what kind of optics, or why do you need also a lot of optics for laser?
Well, I'll show you. For that, just to kind of compare
Okay.
like what happens with different types of light, right? So I mentioned before, like laser light essentially lines up all the waves, or it attempts to line up all the waves very closely. So you get just one frequency and it's all coherent, right? And just to kind of compare, like sunlight is putting out all different frequencies, okay? And light emitted from one section of the sun is going to be out of phase with light from the other section of the sun, and it's all just totally random. So we call that incoherent or non-coherent light. And even like an incandescent bulb, which might have very narrow range of emission, or like an LED bulb, which basically tries to mix like different colors to give you what appears to be kind of like the typical incandescent. It's still going to be totally incoherent light, but it's just sums up to give you the color that you like. But yeah, this is kind of just to compare like what the waves actually look like when they come out of a laser is they try and line up together, so that way that's what gives you the very intense output beam from a laser.
Why
Now
is it
you
intense? Because on this picture it looks like they are not building up on top of each other, or are they?
well they are, yeah. It's just because when I have two waves that are in phase and they exist in the same area of space, then the
Oh,
electric field and the
okay,
magnetic field add together.
okay,
Yeah, so that's called superposition.
okay. But so on this picture, better picture would be like they are like on top of each other.
Yeah, yeah. So we
There should be
basically like,
one like zoom of this or something like that.
yeah, exactly. Yeah. So like, I'm drawing here
Mm-hmm.
with my mouse, like really big, wave crests or something like this.
Okay,
That would be the idea. Yeah. Yeah.
okay.
Okay. So when you actually get
Oh,
into the cavity, this is actually what's going on inside of a cavity. So this is just an example with a ruby laser. And so um, inside this cavity, there's a lot of stuff going on. Okay. So
when you say
essentially,
cavity, what does it mean?
so when I say cavity, we mean like this chamber
Mm-hmm.
and all of the stuff inside of it.
Okay.
And this rod, and this rod is some material that is very likely to exhibit laser light if it is operated correctly. So, so Ruby lasers, and I'm just going to say this is a little simplified just to, kind of give you an idea of what's going on inside of a cavity. But in this cavity, you have, this really unique high intensity flash lamp. There's going to be a power supply that delivers an electrical pulse to the flash lamp. So it then flashes a very bright pulse of light. And then that's what initially excites this ruby rod. And then there's the spontaneous emission. So just the random emission of photons. And those photons start circling back and forth through the cavity. And that's what causes you to eventually build up to very high intensity light, where all of these waves start to be in phase with each other.
So do you need to like flash this lamp in specific frequency to be like in sync with the photons inside of the rubin, or?
Yeah, so I'll actually show a graph of what that looks like. But yeah, essentially what happens is it depends how you would want to form a pulse here. So this would be for a pulsed laser, because we're actually going to we're going to flash this at a very to a very high intensity very quickly. And that's going to allow the pulse to build up. And then that pulse will build up in intensity and then eventually die off. And so this will give you a pulse of light. However, let's just say that this were running at DC and you just had a very high intensity lamp in here. You could actually run this at DC and then get continuous wave out. So it just runs continuously.
Okay, but the intensity will be like smaller, or?
Yeah, the intensity will be at whatever the average power is for that wave. Now, we don't normally do that with lamps because lamps are really inefficient. Like, your typical high intensity flash lamp is not going to be anywhere near 100% efficient. And so if you're doing something with continuous wave output, then you would actually do it with like DC. Like you would do it with like a diode. So diodes are much better because they're a lot more efficient. You don't have to like take electricity, convert it to light in a lamp, and then convert the lamp light into laser light, and then wait for only 5% of that laser light to actually leave through this mirror on the right. So you see what I mean?
I'm thinking about, you mentioned in the rubin there will be some oscillation inside of the rubin. So basically, how this happen?
Well,
why
because
there is
you
the
have
oscillation? Because they reflect from the edges of the rubin, or?
That's exactly right. Yeah. So we have 100% reflective mirror at the laser wavelength. And if a photon is emitted here in the center, and let's say it starts traveling left, it'll reach the mirror, reflect off the mirror, and then start traveling right.
And always when it is traveling, it can generate or excite some other photons.
Exactly right. Yes. So one photon can reflect here, go this way, turn into two. Those two can turn into four. The four can turn into eight, and so on and so forth. And it just cascades back and forth over and over again.
And are not they losing energy when they like excite the other photon?
Well, there are losses in this material. However, if you flash this to high enough intensity, the gain that you get overcomes those losses.
Okay.
And so if you didn't flash this lamp at high enough intensity, you could have some initial oscillation, but eventually it would die off.
So basically, you excite the electrons on like higher energy, so they can like collide with number of different electrons, or I don't know what is going to.
You would essentially get more light out of more excited electrons.
Okay.
Yeah.
And then the other side of the ruby is like open, or it is also half reflection, or?
So it's a mirror, but a lot of the diagrams that you'll see from some websites, they'll say, oh, it's a 50% reflective mirror. That's not always the case. Usually if it's two mirrors, it's actually like 100 and like 95% or 98%.
So only like 5% of the light goes out?
Yeah, exactly.
And 95% is used to excite all the other stuff inside.
Exactly.
And if you use like I don't know, 50%, then it would not work?
There's a chance that it might not work. And
Okay.
the reason it might not work is because maybe you don't build up to high enough photon
Mm-hmm.
density in here to actually overcome that threshold to where you get a strong pulse of light out.
Mm-hmm. Okay, interesting. What else
Now,
we have here?
yeah, so what else we have? We have our power supply. This is going to have our switching circuit in it. This cylinder where all of this stuff is encased, we like it to be reflective. So like, let's say any photon that's emitted here inside the ruby kind of, comes out the side of the crystal, it can reflect and come back in.
Mm-hmm.
Then we also have, the switch is usually controlled by some other circuit, some other like control panel. Maybe you have like a little keypad or something, whatever that is. This allows the user to control it. And that's essentially what's happening in here. It's a little oversimplified, but I think it works. This is a good picture because, it kind of shows like the structure of what happens inside of a laser cavity.
Mm-hmm. And I have another question. So, uh, how do you control which direction these photons will go? Because if they are like in sync, they have to go like in specific directions.
That's right. Well, they could technically go any direction, right? It's just that you have a hole here in the right side of this cavity, right? And this hole is where the light can exit.
So
And so
basically,
it's
it goes all directions, but out it goes only with one direction.
That's right. Yeah. So technically, like there's light everywhere in here,
Mm-hmm.
right? And going in all directions, but the only light that you care about is the light that
Mm-hmm.
actually comes out of this
Okay,
hole.
I understand. I
Yeah,
thought that inside of the Ruby, it only can generate the waves which will go one direction. No, it goes all directions everywhere.
that's right. It goes
Okay.
all directions. Yeah.
Okay.
Okay. So we can already get kind of a shopping list here, right? We got our power source. So I mentioned electricity. Could be another laser though, right? So like just going back here, instead of this flash lamp, like you could have a lens here, and then you could fire another laser in from the
Mm-hmm.
left, and that laser could be the exciting laser.
So is it more efficient or
No, just for some. So for some lasers,
some
it
materials you
is
can excite only with
yeah.
light? Okay. Okay.
Well, it's the difficulty in like, can I actually get to high enough intensity
Mm-hmm.
at the
Okay, I
exciting
understand. Mm-hmm.
wavelength with a flash lamp? And if the
Mm-hmm.
answer is no, then well, I can use another laser to do
Mm-hmm.
that. So then this crystal right here, the ruby, is something that in the laser community we would call a gain medium.
Mm-hmm.
So meaning it's the medium where all of that light gets generated, it gets amplified.
So what are the other kind of materials where this light can be generated?
Yes, there's a long list, and well, we'll get into that in just a
Okay.
moment. Um, but then we need our chamber or our cavity,
Okay.
and then we're going to have some mirrors, and then we have what's called an output coupler. And so
About mirrors, how
this,
do you manufacture the mirrors? Are they like some special kind of mirrors, or are they going to melt?
yeah, well, technically, yeah, you can damage mirrors, even though they may be nearly 100% reflective. They're not fully reflective. There is some slight absorption even at the reflective wavelengths. But essentially, they're manufactured by just depositing some material, whether like through
Aluminium or what
evaporation.
different kind of materials?
It just depends the wavelength where you need it to be highly
Oh,
reflective.
okay.
Yeah. So it could be an alloy, could be aluminum, right? If it's like, let's say you're operating in the visible range, could be some other thin film. Really just depends. But yeah, it's just deposited onto like quartz or glass, whatever the material is going to be, and then you just stick it in here, and that's it. So Thor Labs is one company that sells all sorts of different mirrors that are designed to have high reflectivity at a specific range of wavelengths.
Okay. So these mirrors are not directly deposited on, for example, this ruby. You can have them like in different places.
Right. Yeah. So just for maintenance, it makes sense to have this mirror be like its own component.
Mm-hmm. Okay, I understand.
Yeah. Because let's say, like, for example, this ruby rod gets very hot and then cracks, which can happen. So for some lasers, you actually have a liquid cooling system that cools all of this down, including the crystal. Yeah. So at very high power, some laser crystals can crack. And so you have to have a cooling system. Well, all of those are separate components.
Okay. What
So,
is
and
next
that's
on the
when,
list?
okay. So output coupler. So technically this 95% mirror is our output coupler,
Why is it
but they're
called
all,
coupler?
uh, that is just a way of saying it couples light from the inside of the cavity to the outside of the cavity.
Okay.
Yeah. So it's overly fancy name. Let's say. So we have an output coupler, but there's different types. And then I mentioned like cooling. So, we want to monitor the temperature. We want to be able to, trigger when do we send in water to cool it, or when do we turn on a fan, whatever the case may be. So we have some thermal stuff. But yeah, so the reason I show this is to show that, you have waves that build up inside of this cavity. Okay. And that determines what are called modes that you can actually excite. Okay. So if if any of your listeners know about digital signals, right, like a digital electronic signal, you'll know that that signal is made up of multiple frequencies. Okay. And inside of a laser cavity, we kind of have a similar thought process. There are many frequencies that could build up to high intensity inside of this cavity.
So
And
it
I've just kind
depends
of like,
on the length of the or distance between the mirrors, for example.
yes, yes. However, only some of those waves will actually generate very strong laser
Mm-hmm.
light. So, like, let's say like a 1 meter wavelength, right? That's a very low frequency. Well, if my laser only responds to visible light frequencies, then a 1 meter wavelength, frequency will not generate any light. So while technically you could have an infinite number of frequencies that are allowed in here, only some of them will actually generate laser light.
Mm-hmm.
And so the ones that actually do that will depend on the gain medium. So the material that you actually put inside of this laser. And so also how you locate the mirrors kind of determines where the light is emitted. And there are different types of cavities here, right? So you can use concave lenses, kind of like I've shown here. You can use
Mm-hmm.
like a concave convex lens. You can have, this flat lens, or this flat mirror with a concave mirror. So there are different
Huh? I
configurations.
didn't know this. I thought they will be like flat mirrors all the time.
So I'll show an example where you actually don't have flat mirrors later. But yeah, you don't have to have flat mirrors. In fact, here with the two concave mirrors, like the gain medium could actually just be this really small crystal that's just here in the center,
Mm-hmm.
because that's where all of that light is going to get focused and build up to high intensity. Right. In these stable configurations, you'll build up basically like a circular beam. Whereas in the unstable configuration, you actually tend to build up more intensity around the edges. And so you get something that looks kind of like this in the lower left,
Mm-hmm.
where the cross section is more like a ring.
I'm lost.
So sorry. So okay, so in the stable configurations here in this column, right? This just tells you like where you need to line up the mirrors
Okay,
based on.
let's explain what is on these pictures. So these are the mirrors which are on the ends of the ruby, for example, and ruby
Yeah,
will be
exactly.
somewhere between the mirrors.
Mm-hmm.
And mm, if it's like super simple, then you would have flat mirrors,
That's right.
and the light would be just traveling between the mirrors, and inside of the ruby it would be generating new and new photons.
Mm-hmm.
And basically it does not really matter how far these mirrors will be from each other. You don't need to have the lights in phase or something. It's not necessary, correct?
Yeah, I mean, over time they'll line up in phase
Oh, okay.
naturally.
I didn't know that.
Yeah.
So will they be in phase even if the mirrors are not in like wavelength position or something?
Right. So what will happen is, maybe just a slight change in the position of the mirrors, could cause you to emit at just a very slightly different wavelength. But those wavelengths, as long as they're within a certain range, then they'll output laser light.
Okay.
So, yeah,
So basically, we don't have to use flat mirrors. We can use these curved mirrors because then we can focus the light into smaller spot and get like much higher intensity uh,
yes,
excitement inside of the material.
yeah, exactly, yeah.
Okay.
And also think about it like this. Let's say you have a photon that starts in the center and maybe it travels off at an angle.
Mm-hmm.
If you have a concave mirror, you can capture that
Mm-hmm.
photon, and then it's going to go back through the cavity.
Mm-hmm. Okay.
And
And so what is difference between stable and unstable?
so that's going to tell you like where the high intensity light builds up in the
Oh, okay. So
cross
stable will
section.
be inside of the material, but unstable it means it's going to be away.
Yeah, so unstable means it's going to be more towards the edges
Mm-hmm.
of the material, whereas
That's what
stable
you
is going to
show on the
be,
picture.
yes, exactly. And they never come out perfectly circular. It's, kind of might be a little oblong. And, of course, there's imperfections on these mirrors. There's imperfections in the crystal, but, you try and get to a nice circular spot.
Okay.
So now the materials, this is the fun part, right?
Ah, nice pictures.
so, so here on the left, okay, I'm showing a laser or a dye laser. But this type of setup that you see here could really be used for just about anything, right? So here, the really intense spot where my mouse is, here in this area is where the laser dye is at, okay?
Mm-hmm.
And so this laser dye is being pumped with a green laser, and then it's outputting in this orange wavelength.
Can you really like look at this open laser?
This is from a side view, and you can actually see that the the laser light is actually scattering off of air and dust in the air, and so that should just show you how intense these lasers can get.
But the center of the laser it has to be like very bright, isn't it?
You should not look at this
Okay.
directly. There are special goggles that you can buy that will protect your eyes
Mm-hmm. But I mean
from
like the place where the light is generated.
right.
There, yeah.
Yes.
So this should
Yeah.
be like it is very bright, isn't it?
Yes, it is.
Can this also damage your eyes?
Yes. Yes, it can.
So it should not be open. This is just like they just
No,
a
it should.
picture and close it.
This is just take the picture. Yeah.
Okay.
Yes.
So this is not how you
And
see it in your lab.
no, it should not be doing this in your lab.
Okay.
Like all of this would normally be closed,
Same the
right? They
second picture,
close
I guess.
same thing. Yeah. Again, this is just kind of a demonstration, you know. But here, this is just a gas, but it kind of operates on the same idea. But here with the gas, normally what you're doing is you can see the electrodes coming in,
Mm-hmm.
and then there will be a discharge electrode here inside of the gas tube, and then of course the light builds up back and forth and then emits. And it's actually some common gases that you can use. So down here I've written CO2, nitrogen, helium. You can do helium neon blend. So some simple gases can be used. Nitrogen was one of the main ones that I used when I was doing stuff, but a lot of industrial lasers will use CO2, carbon dioxide.
Mm-hmm. Why this whole bulb is not closed in some like reflective
Well,
environment?
well, normally it would be.
Okay. So this is
Yeah,
only for
normally,
picture again.
yeah. Again, this is only for the picture.
Because then efficiency goes much lower if okay you are losing a lot of light which can be used to make the laser
Yeah,
stronger.
exactly.
Okay.
Yeah, yeah. So normally this is probably a helium neon laser tube, and so you would normally put this into an enclosure,
Mm-hmm.
and then that enclosure, like you won't see any of this stuff behind it. It's all black, and then like inside it'll be reflective.
Mm-hmm. Okay. And when we go to the first picture, so what are the other things? What are used there? There are some lenses or
Yeah, so there are some lenses to create a parallel beam. You probably have a polarizer here, so to essentially only select waves that are oriented one specific direction.
is it
So
going to
meaning the
like make the laser stronger, or why we would like to polarize the?
no, it actually makes it less intense. However, polarization is needed for some experiments.
Mm-hmm.
So, like if you were doing something with like material characterization, let's say, you would actually want to be able to control the polarization.
Mm-hmm.
And so that's probably what one of these plates is. Here, I'm not sure what this would be on the end. This could be a power analyzer. It could be anything really.
How safe are the glasses? What do you have to wear when you are in this kind of lab? Can you trust them? Like
Yeah,
fully trust them?
they are designed to provide full safety up to a certain power level for a direct hit to the human eye.
Do you test the glasses before you use them?
You're relying on the manufacturer. I mean, if you want to test them, you can. Just don't test them with your own eye.
So what if you buy glasses for different wavelength
They're
by
only going to
mistake?
protect. Yeah, right. You have to look on that package because on the package it will say like it provides this much reduction. So it could be factor million reduction, makes the light 1 millionth as intense. And it'll only be in a certain wavelength range that they'll guarantee.
You need to be pretty sure you use the correct glasses.
Yeah, exactly. Well, and the practice is you try and buy one pair of glasses for the lasers that you have in your lab.
So you put it in front of the laser and you measure
That's
power
the
after the glass. Okay.
that's the one that's the one you use, right?
Okay.
And so there are meters. There are actually meters you can buy that respond to specific light waves or light colors that you
Mm-hmm.
can use to measure the energy in the beam. And so if you wanted to, you could measure the attenuation that's given by different glasses.
Okay. And
Yeah.
are they like dark or they don't have to be necessarily dark
they,
glasses?
they they can be very interesting colors. So like the ones that I used to protect against UV light, because like I said, I was using a nitrogen laser. Nitrogen operates in the UV. So the ones that I was using to protect against UV light, those ones looked orange. So like you're seeing orange all day.
Is
Some of
it
them are clear.
is it problem sometimes? Like if you
You
see
get used
everything
to it.
in one color when you
You
make
get used
nodes
to
or
it.
something?
You don't. Well, I can assure you, you don't go insane. You do get used to it. So.
Then you go outside, you put the glasses away, and like, oh, what a wonderful world!
Well, there is that, but also like we were in a basement because we're using high power lasers, and so the building we were in was a 5-story building, but we were in the basement because they don't want to put that laser in the fifth floor, and then have the beam go out the window and strike some guy in his office in a skyscraper 5 blocks down the street, because they will go that far and they will do damage at distance.
Wow.
So you put them in the basement where there's no windows, and so I'd go in the morning and I'd do all my work with seeing orange for most of the day, and then I'd leave and it's nighttime. Yeah, so that's what the life of a laser technician is like, especially if you're using high power lasers. So
So
on
liquids.
the
Okay, and inside of the liquid laser, what would be there?
so it's literally just a dye. It's just a material. So the most common is called rhodamine. There are
Is it
different
what is it? It's
shades.
like water, or how does it look?
Um, it just has a certain tint to it. It's just a liquid and it has a certain color.
Mm-hmm.
And there are many different types of rhodamine dyes. So like you can purchase rhodamine dye. I think you can buy it from. I've never bought it from Sigma Aldrich, but they're a big chemical company. They might be able to supply it.
Wow.
There are other companies that will just sell it to you.
Interesting. Okay,
Yeah.
then gases and then solid. So solid, I guess
Yes.
these are the like in the laser diodes. Yeah, laser
Yeah.
diodes. I
So
see it there.
so what I've seen, yeah, what I'm showing here on the right is like the structure that you'd have for like a semiconductor laser. So you can do this with 3.5 semiconductors. 2.6s are also common. So when I say 3.5, I mean like group 3 and group 5 on the periodic table.
Mm-hmm.
2.6 is group 2, group 6.
Mm-hmm.
But then
So
there's
it's because then the electrons can jump to specific.
yeah,
Okay.
exactly. And you know, remember what I said, theoretically, any material could do it. It's just how much light do you actually get out before you destroy the material? And, you know, is that practical for you? And so these are the semiconductors and then the crystals that tend to operate very well in practical systems.
So what is difference between standard LED and laser diode?
Yeah, so a standard LED doesn't necessarily have light circulating back and forth in this particular active region
Mm-hmm.
to give you this buildup of photons at one specific wavelength.
Mm-hmm.
What you're actually seeing in an LED can actually be a really broad range, whereas the laser light is going to be a narrow range of light. Now, in both cases, they look red, right? The human eye just interprets it as red or blue or whatever color it is, but it's that range of wavelengths that make up that red color or that make up that green color.
Can we
Those are going to
compare
be
the range? It's like I don't know. Let's say LED will have I don't know hundreds.
so I'll actually show an example of what like the power output can look
Okay.
like.
Okay.
Yeah. Okay, so I mentioned that different uh, frequencies can experience the gain provided by these materials. Okay, so like we call those modes, and all of those different modes have different frequencies. And I mentioned before, right, the distance between these depends on the length of the cavity, right? So if I make the length really big, then the distance between these is going to get really small. So like in this laser here on the left with the dye, this is let's say it's a 10 centimeter cavity. You know that means you're going to put 10 centimeters down here in the denominator of this of this equation. So you're going to get like gigahertz mode separation. Well, when you're operating at terahertz frequencies, because that's what visible light is operating at, so like 300 or 400 terahertz, that means you get a lot of modes that pack into this region where you can actually emit light. So this green region tells you the region where, for a practical system, you can actually get laser light out. Okay. So what happens is typically the one near the center or the very small number near the center are actually going to build up to high intensity and output light. And so they're very similar color, right? Because if you're dealing at 300 terahertz, but your modes are separated by 1 gigahertz, how many modes can you fit in there? Well, it could be hundreds of thousands of
Mm-hmm.
modes. So the ones that are very clustered near the very top are the ones that are going to experience the most gain and
Mm-hmm.
are actually going to
Okay.
contain all
So
of the
I
light.
just noticed. So the modes are only like the very thin lines which you have there. And if you have
Yeah,
this
so
delta frequency, then you can put there like many of these lines, these modes inside of this delta F.
yeah,
Okay.
exactly. And each mode is a wave, right? It
Mm-hmm.
has a wavelength that
Mm-hmm.
fits into the cavity.
Okay. So it is important basically what is the length of the chamber or distance between the mirrors basically.
Yeah,
Correct?
exactly. And so this is one of the reasons that like a semiconductor laser, so like this structure here, it's so easy to control the number of modes because it's so small,
Mm-hmm.
right? I mean, you can fabricate a semiconductor that is the wavelength of the light you want to
Mm-hmm.
emit, right? So you're basically just going to have one mode if you
Mm-hmm.
want. You can get down to one mode. And then there are ways to actually control, like, let's say you do have only, I don't know, let's say you only have like 2 or 3 modes here in this gain curve. Like you can actually select for certain modes to come out.
So how do you select this specific mode inside of this like specific length?
Yeah, so that can be done with a filter. It could be done with a diffraction grating.
Oh.
Actually, a diffraction grating is a filter, but I mean, technically you could do it with a filter, but really the standard way to do it is with a diffraction grating. So a diffraction grating is basically it's a bit hard to explain, but it's basically like a set of wires that are fabricated onto a reflective material. And when the light comes in, it splits up light into its colors. So that's how you get different modes to come out at different directions. And that, yeah, so that's if you've ever taken a physics class, you've probably heard about like slit experiments, double slit experiments, or diffraction grating experiments. It's something that you'll actually do like as an undergraduate, like in your physics 101 lab class. You'll play around with these gratings because they can be fabricated with, just pretty standard machining techniques. And then you can use that to split up white light into, red, green, and blue.
Yeah, I
So
only
like
remember the experiment with I don't know English word for this.
prism.
Yeah, I think it's prism. Yeah.
Yeah. So you could do the same kind of thing with a prism. Yes, prisms are also used.
Mm-hmm. Okay, so you kind of always need to somehow filter all the other frequencies, so you only work with the one specific which you want.
Yes, you can do that, but there's also a technique called mode locking, which I'll briefly explain later, which actually takes advantage of the fact that you have millions and millions of, possibly millions of modes here inside of this gain curve. And then by lining all of those up, you can actually get to extremely fast pulses.
Mm-hmm.
So when I say extremely fast pulse, we're talking femtosecond pulses. And so just for reference, like for visible light, let's say green light, the amount of time it takes for the electric field to oscillate between its high and low state, because remember, it's electromagnetic field is a wave when it's in, light wave. So the electromagnetic field is vibrating or oscillating, right? That oscillation period is on the order of femtoseconds.
So these
like
are
it
the
is
terahertz or what do you...
no, these are we call them femtosecond lasers. I mean, all light waves are operating at or in the visible range, I should say. Like visible light, the frequencies are like around 300 or 400 terahertz.
Mm-hmm.
Just depends on the wavelength, right? But that frequency has a period associated with the electric field. I mean, so how fast does the electric field move up and down, right? And so with femtosecond lasers, you can actually get the time it takes to deliver all of that energy to happen within one oscillation of the electric field.
So these are basically 1 divided by the frequency. That's the time.
Exactly. Yeah. So you can get to extremely fast lasers.
How can
and
you
then
build
there are
electronic circuit which will create so short pulse?
That's the thing. You're not doing it with the electronics. The electronics play no role at some point.
Okay, I'm curious. So let's continue.
It's all optics. So there, like I had mentioned before, there are two modes, right? And so I mentioned mode locking, right? And what mode locking, this technique that you use to get to really fast pulses like this, what it actually does is it creates this series of pulses. Okay, so instead of having just a wave oscillating continuously at fixed power, you'll notice that this power is very low, maybe 10 watts. What pulse lasers do is they pack all of that power into a very short time and then deliver it very quickly. And so you can get to very high power outputs. So kilowatts is a typical number for a lot of industrial strength lasers.
How do you do that?
They can get even higher. Yes. So that's the fun part, right? So I'll go into some examples here, but this is the typical type of system that you have and how big they can actually get. Okay. And all of the optics and the electronics that go on to give you like these very fast pulses and these pulse trains are all contained inside of this box here in the foreground. Okay. So this contains all of the laser light. All of the laser light is generated in here, and then it gets output through one of these windows. Okay. And then you have this entire control block here in the background. And this control box provides power. So it's got a huge power supply in it. It's got the water pump and return lines in it, because this is actually a water-cooled system. It has to supply, I write many amps of current here because it's going to be a lot of current delivered really quickly. And then these switching circuits are actually relay based. It's just that typical MOSFETs can't provide the power fast enough.
Mm-hmm.
So you're actually going to have a MOSFET that switches a relay, and you can actually hear the clicking of that relay as it goes back and forth. So those relay based switching circuits, they can provide 10 or 20 hertz, let's say, pulse repetition rate, meaning like you would be delivering like 10 of these or 20 of these a second.
Mm-hmm.
If you wanted to, you could do that.
But it says that like 12.5 nanoseconds.
That's right. So now that's when you get to another technique
okay.
called mode locking. So when you're doing mode locking, then you can get to these extremely fast pulse rates. Yeah. So the energy here, you'll notice, is really low, but because we're packing all of that energy into a very short time period, we get to a very high power. And like with this particular system, I actually used this system. Okay. So this system, if you're getting it down to, let's say picoseconds worth of pulse, you can actually get to very high output power.
Wow. How do you use this, or where do you use this power? Still for some experiments, or?
So I was using it for
you
some
were burning
experiments.
some stuff.
No, I was actually using it to pump nanoparticle lasers. So I'll show some examples of nanoparticle lasers at the end. That's where the real fun is, because that's where everything gets totally randomized. And it's a total shift in how to think about how to build a laser. But it's actually a laser that you yourself could technically build. So we'll get to that.
What are these
later.
black balls on the top? Are they like you close the opening or something? I don't know.
Exactly. Yeah, that's to open and close the window.
Okay. So then you are sure it's closed. It's closed. I don't need to worry about this one.
Exactly. Yeah, that's what you grab. And you open and close the window. And then you'll notice there's even an emergency shutoff here. So if things really go crazy, you have an emergency shutoff on the power supply.
So how big is this thing? It's like
it's
2
big.
meters or?
Yeah, it's
like table.
Yeah, so I think the length here is almost a meter, probably 3/4 of a meter for the laser box, maybe a half a meter. So Google XPLA ND YAG laser. So up here, this is the type of crystal, so neodymium, and it's doped, or it has impurities of yttrium, aluminum, and garnet. So there's all these impurities that go into building this laser crystal out of neodymium. So yeah, that's just kind of a example of a actual laser system that you would use for. I mean, this thing will certainly ablate metal. It will damage glass. It will make you go blind if you look directly into it. So definitely don't do that. You can use this as a pump for other lasers as well.
So you can even damage glass? Because glass is transparent. So where the energy...
I've done it regularly. Well, this is outputting at UV wavelengths.
Okay.
So glass has...
So some glasses are not transparent for some light.
Exactly. Yeah, if it's not transparent at UV, then yes, it will damage the glass.
Okay, so the lenses inside, they always have to be also built for specific wavelength?
Exactly, yes. So if you're operating with this type of machine, you would use quartz.
What would I use?
Quartz glass, not, yeah. So it's a specific type of glass. But yes, you would use quartz. QUARTZ.
Okay.
Yeah. So that's what you would use. There are other glasses. Glass is a broad range of materials, but there are other glasses that you could use that would be transparent to these wavelengths at 355 nanometers.
Okay, let's move to the next slide. What do you have there?
Okay, so here's what I was referring to earlier, where you have, like, in the semiconductor laser, right? You could have multiple modes operating, but if this thing is small enough, you can actually select for a smaller number of modes, kind of like what's shown here. Okay, so this is just kind of a simple example of what the power output might look like from a semiconductor laser. Now with the LED, what you're actually seeing is you're seeing stuff in this range where the peaks are, but you're also seeing all of the light around in the edge in the background. Okay. And so with the laser, it's just that some of that light builds up to really high intensity. Okay. And the structure here, it's a bit more complex than what was shown previously. But this particular type of laser is called a vertical surface cavity surface emitting laser. It's VCSEL, or it's VSCEL. I always get the C and the S backwards in that acronym, but it's a specific type of laser where essentially you excite the active layer, and then light moves back and forth between these mirrors. And in the process of moving back and forth, eventually it leaves through this top electrical contact. So this top electrical contact either has to have a window in it, or it needs to be made from a transparent conductor like FTO or ITO.
Oh, I didn't know that. You can have transparent conductor.
That's right. You can have transparent conductors. So your touchscreen uses transparent conductors.
Right.
Yeah.
Okay, how do you build the electric mirror?
Yeah, so it's essentially depositing different semiconductor layers in succession to give you high transparency only at specific wavelengths. So within the region that you care about, that you want to transmit.
So that's why there are three, because there are basically three peaks in the graph.
No, it just depends on how much absorptivity you want to have, or how much attenuation you want to have outside of those other bands.
Okay.
So and that's a bit more of a, I guess you could say it's a little more of a complex discussion, because you're essentially trying to cause strong interference at these specific wavelengths, so that you can have a high intensity pulse that gets reflected off of these mirrors. I probably could have think I could explain that a little better, but
I'm essentially thinking, like, why there would be like more mirrors? Because does it mean they are not perfect, or so?
Well, sure, yeah. One stack of this material is probably, maybe it doesn't give you 100%.
So that's why you may need like more, so you reflect most of the light.
Yeah, because remember, we want the emission to happen here at the bottom. We don't want it to happen here at the top. We want total reflection up here at the top. And so then it travels back through the active layer and then through the bottom contact.
And is it still going to like excite the stuff inside of the active layer, correct?
Yeah, exactly. Okay. Right. So yeah, some photons are going to travel up, and then during this travel they reflect and then come back and then excite more.
Okay. I think I understand a little bit.
Yeah. And so remember, you still have the mirror down here on the bottom too, right? So not all of the photons are going to emit through this bottom surface, right? If this is like 95% reflective, well then essentially you can interpret that as a given photon that leaves the active layer traveling down has a 5% chance of leaving through the bottom contact.
How do they control like power of lasers? Can you control it, or?
Yeah, so you kind of control it, right? Because if in this arrangement for a given input current or a given input power, if I don't get enough power out, what do? I just turn up the input power, right? That's one way to do it. But then let's say I don't want to turn up the input power. Well, then I have to re-engineer this cavity so that I get lower losses, meaning that like I have less absorption of my photons that I want to emit as they travel through the cavity.
But basically, you can't really control the power once it is built, can you?
Well, yeah, you would do that by turning up the input power, right? That's how you could control it. Um,
Okay.
and then also remember, like this comes out into a beam, right? So that beam has some size. So I could focus the beam.
Mm-hmm. Okay.
That's one option.
So in the other kind of lasers, can you control power of the?
Yeah, so it's the same principles. It's really the same principles, right? I turn up the input power, or I re-engineer the cavity so that fewer photons are lost during this back and forth travel around inside the cavity.
Mm-hmm. But basically, the
So that
photons they always have like same energy.
the individual photons do. Yeah. So what that means is that this emission, if I want stronger emission, then I need to have more photons
Mm-hmm.
that build up in phase and then leave down here through this bottom surface.
Or you need to focus more.
Yeah, so then I can take that and I can focus it
Mm-hmm.
more, right?
Okay.
So now
But
I packed all of those photons into a smaller area.
okay. Okay. Let's move to the next one.
Okay,
Oh.
so this is the fun stuff. Okay, so now we're getting into output couplers, right? So how do I actually like control the light coming out of the surface? So like a lot of stuff that you see on lasers online will just mention the passive methods, right? Where I have like 95% mirror, right? I basically have no control over that. Okay, I can't really control it because I can't adjust the reflectivity of the mirror. Once you build the mirror, it's 95% reflective, and assuming it's never damaged, it's always going to be 95% reflective. Okay, so the dynamics in the cavity will determine how the light behaves as it pulses out of that cavity, or if it just operates continuously, and then that's going to determine the power output. However, there are ways that you can actually switch that cavity to be open and closed. Okay, you can also control the different wavelengths of light that come out using a grating. So I mentioned this before, right? So the really simple method is just the mirrors here,
Mm-hmm.
right? It can get a little bit more complex when you have multiple modes and you can select different wavelengths from the cavity. Um, then there's also something called Q switching, okay? And there are methods for essentially opening the cavity really quickly and then closing it.
Mm-hmm.
Okay. And then there's actually a device called a Pockels cell, which you can actually use to electrically open and close the cavity.
But if you just
So that
open and close it, you still get the like maximum peak just for very short time. Correct?
exactly, that's the idea. Yeah. So it's so you're letting out the light very quickly, and then all of that light comes out and gets packed into this very short period of time, and then it drives off, and then it drops off.
Mm-hmm. But you are not changing maximum like power from the pulse.
Well, that depends on how deep this modulation is, meaning like how open do you make it?
Mm-hmm. Ah, okay. You can even like make it. Oh, okay, I understand.
Yeah, so that's not necessarily done with a Pockels cell. There's actually another way to do it with absorbers.
Mm-hmm.
But yeah, you can essentially modulate either the polarization and let light out that way. Um, excuse me, you can let light out that way, or you can just fully open it and then let the light come out, and then now you're controlling the peak pulse based on the amount of energy you put in. Or if you have an attenuator, right, an attenuator can do that as well. But a Pockels cell, if you think about it, right, I mean, it's essentially like an attenuator, right? It's essentially saying that I don't want any light to come out of this cavity. So anything that tries to come out, I'm going to essentially attenuate it and keep all the rest of the light inside the cavity.
Mm-hmm.
So it's kind of a simplistic way to think of it. But the point of using a Pockels cell is that it's electrically driven, right? So I can have a circuit here that applies this switch, that applies switching action to the cell, and then the cell is going to open and allow light out, and then it closes, and then no more light is allowed out.
And how does it work? Is it like some kind of material which you can make like semi-transparent by electricity, or how does it work?
Uh, that is essentially that at a very basic level. Yes, that's essentially
Okay.
what's happening. So it's a specific type of material. Now, this is something that they never tell you in, I think, in electronics, because well, frankly, most electronics does not use this, but there are materials that are called nonlinear materials. Like, so obviously semiconductors can be nonlinear, but they can also be nonlinear to an electromagnetic wave. Okay. So what that means is that you can actually modulate the refractive index. So refractive index for all the electronics people out there is just the square root of dk. Okay, so we know what the dk value is for like a PCB substrate.
Mm-hmm.
dk value is just the dielectric constant. It's the same thing inside of a capacitor. So in optics, we normally refer to the refractive index, which tells you how light bends.
Mm-hmm.
Okay, so in a Pockels cell or in a Kerr cell, and there are other types of cells based on the material, you can actually change the refractive index
Mm-hmm.
by electrically. So it's called an electro-optic effect. Okay. And in fact, with the Kerr nonlinearity, we call it the Kerr electro-optic effect. And so what that means is that the material refractive index can change depending on the intensity of light or depending on the electric field that you give the material.
And this is interesting. So it is in back of the laser, not in front of the laser.
It could be either location.
Okay.
Actually, yeah, yeah. So this unit, it is actually, it's back here on this edge. But what actually happens is you have the laser head, and then the light is going to come out. It's going to go through a series of reflectors
Mm-hmm.
and conditioners, and then it's going to come out here. So so this is a little simplistic, but it doesn't have to be located here by the back mirror. It can actually be here by the output mirror.
Yeah, but initially I thought it is always in the front. I never thought like, oh, it could be also in back.
Yeah, exactly. Yeah, it could be in the back. Yeah.
Okay. We can go to the next one.
Yeah. Okay, so here is
So
where we can start to
circuit.
see. Yeah, here's where we can see some electronics, right? Okay. So okay, so this is just an example of a Q switching circuit that you would use to control a Pockels cell.
I will stop you for now. So
Okay.
what kind of like power, like biggest power, what we need for like these biggest lasers? Like how much, how many watts, for example?
Excuse me. Okay, so let's think about this for just a moment. Okay, so this, if you have a kilowatt laser, okay, those, and let's say it's 1% efficient or 2% efficient.
Kilowatt laser,
right?
you mean like optical power or like?
Yeah, the amount of optical power that it puts out, right? It's probably going to be like 1 or 2% efficient. So let's say it's 1%, right?
Okay.
And it's a 10 kilowatt laser. So you need a megawatt worth of power. It's a lot of power, right?
So where do you get this power then?
So these are normally running at really high voltage.
Oh.
Or they're transforming that possibly into a high current pulse. It just depends on the driving mechanism. So like with a discharge flash lamp, like you're actually driving that up to really high voltage, but you also have to deliver a lot of current so that you can excite everything in the flash lamp.
So when you have this kind of laser in your lab, do they need to have like special electricity, mains connection or something?
Yeah, I mean, you're plugging, so this one, so I'm in the US, everything is, 115 volts. Yeah, right? So we actually had to plug into 230 for this because this is a European laser. So Explo is a European company. I think they're Swedish. But yeah, all of their stuff operates on 230. And then there's a big transformer inside of this box that actually gives you that high voltage.
Okay. So 230 and how many amps?
Whatever the balance is to get to this required output.
But
right?
Is it like...
I mean,
standard at home is like, I don't know, 20 amp or something?
No, you do have to have a special hookup, right? You're not just plugging it into the wall.
Okay, so you have
so
wires directly
I take that back. You're plugging into the wall, but the wall is on a special circuit.
Okay.
Right? It's not just going into your home circuit breaker.
You need to call your electricity provider and tell them like, put more
You got to call,
wires.
yeah, you got to call the building engineer, and the building engineer has to make sure that they already built the building to even be able to support that much power coming in.
Okay, that's what I wanted
Yeah,
to say. So you
yeah,
will not like plug in this in your room.
yeah. I mean, typical industrial setting could handle this. So like, I mean, industrial settings, they regularly use equipment that's running at, what, hundreds of amps
Mm-hmm.
all over the place, high voltage. Yeah. So any industrial system or any setup that you would use for industrial systems will also work for one of these
Okay.
systems. Not a problem. Yeah.
Okay.
Yeah. So that's all pretty standard.
Okay, we can go.
Yeah.
I see it.
um, so kind of what's happening on the right with these graphs. This should really show like what happens with the Pockels cell and what happens with the lamp, right? So the flash lamp turns on, and the current moving through the gas in the lamp as it's excited, this is assuming you have a flash lamp laser, it eventually dies off. And during this whole time, you have a lot of energy that builds up. It's this inversion graph that builds up in all of these photons moving through the cavity.
So
Okay.
this is, for example of the ruby laser.
This could apply to the ruby laser, yeah.
So the
But
first
let's
one
assume,
is the lamp which was around the. Okay.
yeah. But let's just assume that instead of just a 95% mirror, we also have a Pockels cell.
Mm-hmm.
Okay, so we have a Pockels cell to control when we're going to allow all of this energy to be released.
Mm-hmm.
So very quickly, the losses get reduced.
Mm-hmm.
Okay, and then what happens is all of a sudden, all of that light starts to emit. All of that light starts to transform into stimulated emission. And that's where you get this very fast buildup of the pulse, and then it eventually dies off.
Okay, so basically you turn on the lamp and then turn it off, and this kind of pulse will initiate the ruby.
You can think of it as
example.
like charging up the laser.
And it starts like oscillating and something, and then you release the light. You open the
so you turn on the Pockels cell.
Yeah, but when we tell this cell, I think it's better to explain people that basically you open the laser, correct?
Yes. Well, yes, that's essentially what you're doing.
Yeah.
Yeah, and then we have very high photon flux through the output coupler, and then that builds up to very high intensity, and of course, eventually, this all starts to die off as the number of excited electrons eventually drops to zero, because it will eventually drop to zero because the lamp current eventually drops to zero because the lamp's off.
So for how long it can actually oscillate without the
That's a
lamp?
Great question. I love this question because that is really the key to making a laser that can operate. Okay, like it practically. Okay, remember what I said. Technically, any material could be used to make a laser. The reason many materials don't make good lasers is because this die-off in the number of excited electrons happens very quickly.
Mm-hmm.
You actually want a really long excited state lifetime.
Mm-hmm.
So you want those electrons to go up there, and you want them to stay there for as long as possible.
Mm-hmm.
Okay, so that's going to increase the chances that a wary photon moving around the cavity can then excite another photon through stimulated emission. Yeah, so you want this excited state to last as long as possible.
What kind of time are we talking about?
We're talking from nanoseconds to microseconds, depends on the material. But like the material that I was using for nanoparticle lasers, it actually was relatively short. It was 200 picoseconds.
Mm-hmm.
So we would like it to be as long as possible. But what really matters, or one kind of simple way to compare whether or not a material is going to be useful in a particular cavity, is comparing that lifetime to the round trip time. So if on average, an electron is just going to naturally decay back to the ground state before a photon can arrive to cause stimulated emission, then what do you have to do? Well, you either have to make the cavity smaller, or you have to pick a different material.
I understand, yeah. So basically, you need to keep it up until you get all the reflected photons back so they can excite more stuff.
Yes, exactly.
Okay.
Yeah. Yeah, so that's really the key. That and the materials, damage threshold, its thermal damage threshold. Those two things are really the key to selecting a good laser material.
How the first people come up with all this? Like how they discovered the materials?
Well, you're going to have to go back and talk to Einstein about that because Einstein was the one who originally published something about this in 1917. So he was the one who had originally thought up that this could actually happen. But like a lot of things I think in quantum physics and in physics in general, people will theorize that something happens in you could say like in a quantum system or in an optical system, like in the ideal case. And then it falls upon chemists, material scientists, whoever, to find a material or to build a system that actually makes that a reality
Okay,
or
so
that
first
find.
that was just theory, and
Mm-hmm.
then they
and
someone
then
thought
and
like,
then
okay, let's try it.
yeah, exactly, yeah. And so some of the first lasers were actually operating at microwave frequencies, and they were not called lasers, they were called masers. So instead of light amplification, it was microwave amplification.
Okay, so what is
now
this
now more now more generally we just say light amplification because visible light.
what is this circuit doing then? What do we
Yeah,
have here?
so the circuit, you basically have an amplifier here. It's going to drive a pulse through these transformers. You have all of this in parallel just because you're drawing a lot of power through the secondary side of the transformers, and you have rectifying elements here as you can see with diodes, and it's essentially just delivering really high power. Um, excuse me. It's delivering really high power to the Pockels cell so that it can fully modulate,
Mm-hmm.
and it does it very quickly because you'll notice here in the graph, right? We want to switch this like as fast as possible. So we want to deliver a very high pulse or high power pulse from here, the trigger in, all the way to the Pockels cell. And then there may, in this example, they've got this other, coax connector here to essentially monitor the status of the Pockels cell.
So Pockels cell, it also includes the circuit, or it is basically the part of the laser which also initiate the light, correct?
Yeah, so Pockels cell is an optical component, but it has electrical connections on it. And so you would hook it up to this kind of circuit so that you could essentially modulate what the losses are in the
Because
cavity.
this is interesting because I thought you need this circuit to maybe initiate the light. Because from what we
Right.
were
So
talking about, I understood Pockels cell is the part of the laser which can regulate the power. Like,
yeah, so you're right. It does essentially regulate the power. Yeah, but you'll have a different switching circuit for the lamp, right? Because we want to
okay,
switch yeah.
okay, I understand.
But those lamps are only going to switch so quickly, right? Because the lamp, I mean, they're essentially like vacuum tubes, right? You know how vacuum tubes work. They're nonlinear switches. So not only do they switch depending on the speed of switching is dependent on the amount of voltage and current you put into the lamp, but then they can also exhibit they can basically have like a relaxation oscillation on top of them. So they basically like have ringing, like you might see in like you might see in an unstable amplifier, or like you might see when you have ground downs, right? Ground downs can
Yeah.
create ringing. Um, so yeah, this lamp current could even have ringing on it if it's not driven correctly. So that's a totally different circuit, but it's the same kind of idea, right? I switch it, and it's basically just a switch driver. Could be H bridge, could be half bridge, whatever the case may be, and it's just delivering a lot of power into that lamp very
Yes.
quickly.
Then I still don't understand why this Pockels cell needs so much power. I really thought it's
Yeah,
only going to make some of the material like more transparent or less transparent, or it's going to open the. So why it does need so much power?
they just need a lot of power. It's just because of that effect.
Okay,
You're getting a very strong change in the refractive index properties of this and or in the
Oh,
refractive
okay. And
index.
I thought you only need power to initiate the laser. I didn't really thought you need also power to control it.
Yeah, you do. Yeah, exactly. So that's one part of what actually happens in this big cabinet, right? It's providing power not just for the flash lamp, because this is a this is a flash lamp driven laser, but it's also supplying power for all the other electronics
Mm-hmm.
that go in here. So there are some monitoring electronics. Obviously, there's temperature and stuff like that, and then there's also the Pockels cell,
How
and then this
thick
has
are
its
the
own.
wires between these two devices?
It's a pretty good size cable. It's basically just a conduit that carries a bunch of cable, right? So you don't really see all of the wires, right? I mean, it just plugs in through the bottom, and there's a bunch of wires that go inside into different areas.
Okay.
Yeah.
Okay. So what do you have there next?
Okay. Okay. So let's say we wanted to do something with a laser diode, right? Laser diodes have their own pumping circuits or pulsing circuits.
Mm-hmm.
So this one, essentially, you have a controller that determines the pulse shape that you want to have. Normally, you pass that through a filter. You don't have to do that. But the idea is that you're sending a pulse into an amplifier, and this amplifier is then going to put that out into our laser diode, and then that is essentially going to output. I've drawn a lens here just to kind of show, like, schematically, that this particular lens can be used to actually create a parallel beam. So if you look at some laser diodes, you'll actually see that they have like a little bulb built into the end of the housing. And that bulb is a lens like this that essentially gives you a parallel beam or a nearly parallel beam coming out.
Why they don't build the uh, laser diode with parallel beam going out?
Yeah, well, it's planar, right? And so if you were to try and do that, you would need to like build it out as this big thick stack to try and then put a hole around it, right? I
Mm-hmm.
mean, you could also put like a hole on the end, but even then, like, that light is going to diverge out kind of conically. And so this actually is just a really simple way to do it.
So basically, if someone would like to build this kind of laser, ideally they would like to buy some kind of module which has the optics and also the uh, laser LED built in.
Yeah, so basically all of this stuff in the TX amplifier section, like the 10-volt connection, and then this other connection for the input, if it's being pulsed, um, that is all essentially included
Mm-hmm.
on the laser diode assembly.
Mm-hmm.
And then it's up to you to build the control and driver circuit that you're going to use.
So
Now, this
yeah, go ahead.
this particular circuit, there's a reference clock here because this particular circuit could be used alongside another circuit for like a time of flight measurement. So this is the type of thing you would use in LiDAR. So you have a reference clock that basically times when this is emitted, and it's also keeping track at another circuit when the reflected light is received.
Mm-hmm.
So then that time difference can then be used to tell you what the distance is.
Okay, and what kind of currents and voltages we are talking about here to the amplifier? So
Yeah,
10
so
volts.
so yeah, so for this type of system, I mean, obviously your controller board is going to be, logic logic levels, right? Because it's all digital. Um, excuse me. So for your diode, I mean, something on the order of 10 volts is typical,
Mm-hmm.
and then they could take, again, depends on the power output that they can withstand, but they could take amps worth of current, so it's not going to be too low.
So
Yeah, you
it's
can
not
you
like 10
can
milliamps for LED, eh?
well, again, it just depends what you're trying to do, right? Because, like, there are laser diodes available that can get to relatively high power, at least high enough power that you shouldn't look at them, right?
But
So
the pointer will probably have only a couple of milliamps.
Yeah, exactly. But this type of assembly, without necessarily without the reference clock and PLL, this could also be used for like fiber optics,
Mm-hmm.
like really long distance transmission
Mm-hmm.
fiber optics. And it's essentially the same idea. They're they're just using a diode, and that diode is just going to output in parallel. The only difference is that you may have this lens coupled to a fiber over here. So it just depends how far you want to transmit. But a lot of those fiber transceivers, they're all built into a single assembly because a lot of those are being used like on a campus. So they're not. This isn't like necessarily the type of driver that you'd use to like send data across the ocean, right? This is like from building to building or something like that.
Okay, so let's move to the next slide.
Yeah. Okay. So here's an alternative type of circuit where here, if you wanted to get the higher powers, you could do this with a power transformer,
Mm-hmm.
and then the power transformer provides isolation. So this is for a measure of safety. But yeah, essentially in this, you have this one, it would be hooked up to mains. You have a filter. You have half bridge switching on the primary side, and then that's going to couple to this output side, and then that's going to deliver power to your driver.
This looks
Um,
quite simple.
yeah, they're not extremely complex. What actually gets complex is when you need to have control over here. So in this control arm, where you need to then ensure that you have accurate timing.
Mm-hmm.
So like, let's say you're going to be doing like LiDAR is a perfect example, right? Because like if you're using LiDAR for distance measurements, like a very small deviation in timing due to the speed of light can actually lead to very high inaccuracy. So control circuits are sometimes used, but then you also just have to lay out the PCB properly so that you don't have excessive skew around any of these loops. So yeah, so the eliminating jitter in any of this peak current is actually really important. And then there's essentially a control circuit that can be used for that. And then also this is just monitoring the output power as well. So we'd like to have stable output power so we don't have big fluctuations. Obviously with parasitics and like a PCB, or even like parasitics in this T filter, that could actually create an oscillation on this output that you wouldn't like. So if anyone's familiar with like high power, like buck converters or anything like that, sometimes the parasitics can be enough to actually create an unstable oscillation that then puts you from continuous to discontinuous mode. Usually the solution is just a little bit of resistance,
Mm-hmm.
like 30 milliohms of resistance. But this is also current limiting.
What I'm thinking about is how accurate they can measure the distance because light travels quite fast. So do you need like super special circuits to be able to actually process this very short time?
Right. Yeah, so time of flight circuit specifically, I've never designed, so I'm hesitant to tell you exactly what it's doing. I know that with like, if you were doing this with like radar, where it's, essentially continuous wave and it's not necessarily like pulses coming in time, with radar, what you're actually doing is you're looking at the phase, which you can actually do very accurately.
Mm-hmm.
So the phase can actually, the phase difference, it can be very slight, but it can create a reasonably large difference when you essentially interfere to signals that are different in phase, that you could then tell what the phase difference is. And then from the phase difference, you can then figure out, okay, I know that the difference in time here between my reference clock and my reflected beam that I received is essentially, some value. I can calculate it.
But even if you measure phase, you still kind of measure time, correct?
Yeah, you're just not tracking time,
Mm-hmm.
right? You're just
You are
receiving.
comparing like two
Yeah, because
signals
it's gonna
which are moved a little bit.
exactly, right. And I mean, with an analog circuit, you're not taking samples in
Mm-hmm.
time,
I understand. Yeah.
right? Yeah, so because you don't have to take samples in time, you well, I mean, in theory, you can have infinite time resolution. right? You could figure out time differences all the way down to fractions of a fraction of a femtosecond.
I understand. Yeah.
Yeah.
So basically, you are getting some kind of signal which is telling you how far away are specific things in one row, for example, or something like that.
Yeah, something like that. Yeah. Now, obviously, when the object that is reflecting the beam is moving, then you have another effect, which is the Doppler effect. So it not only shifts the timing, it shifts the frequency.
And then basically, if you would like to get results from these, then basically then you sample that characteristic, that shift.
Yeah, something like that. Yeah.
Okay.
Yeah. So with like with radar, they do it with beat frequencies. So they basically beat the two signals together, and then you can extract a beat frequency just using a filter. And then using the beat frequency, you can then figure out yeah, that's a whole other topic as well.
Okay.
Digital signal processing for radar is
Okay, but still it's good to know that basically they don't sample the input, they compare basically what they are receiving, they compare it what they are sending out, and they get some kind of result based on this, not sampling the. Okay.
exactly. Yeah. So let's go to the next
Yeah.
So this is the type of cavity that you might use to actually generate femtosecond laser pulses. So here in this particular circuit and in the previous pulse driver circuit, the pulse output that you're going to get, or the pulsing, is essentially limited by whatever the parasitics are in all of your different components here, right? And then how fast you can drive it. Okay. So but here, the pulsing is different, right? This is where you start to take advantage of all of the modes that already exist inside of the crystal, that then align them up together. And by doing that, by lining them all up together in time, they will essentially naturally compress to create femtosecond pulses, or very fast pulses.
So basically you are not using electronics but optics to generate these pulses.
That's right. So at some point, the electronics are not fast enough anymore.
Yeah.
And you have to take advantage of the way light, all of these different modes of light can superimpose on each other to generate very fast pulses. Okay. So this is done here in a titanium sapphire laser with an external laser.
Okay.
So we have a pump laser that comes in, and then that pump laser starts the initial travel of light around this very odd cavity. And so this is shown in a very interesting way. Hopefully you can see. But what this does is you have two prisms here on the right-hand side, and then you have a grating here on the right-hand side. And this grating may be connected to a saturable absorber. And the idea here is that all of these beam, or all of the light in different modes that comes in here and comes onto this leg where you have the two prisms. What they do is, by arranging the angles of these prisms just very carefully, what you're doing is you're applying a phase shift to different wavelengths of light based on this angle. And that phase shift is what's going to allow those different modes to line up in time. So they have a very specific phase difference between them. And then once they all come back into here and essentially sum together in space inside of the cavity, eventually they hit the output coupler. And then the output coupler is just a 2% output. Okay, so only 2% of the light leaves at any given time. But as all of these beams travel together, they superimpose on each other, and in time, they essentially interfere to cause a very fast pulse.
Okay, I can't say.
I know there's a ton.
How it works.
There's a ton going on there. I understand. But you have a whole bunch of different wavelengths, right? Because remember, inside of this cavity, there could be hundreds of thousands of modes.
Yeah, I know. But how? I don't understand is how it can generate specific pulse of specific length. Like when you select only this
right.
specific
so
mode.
It's not a specific length, right? Like you don't how do I put this? You don't necessarily have a keypad where you say I want to get 5 femtosecond
Okay.
pulse width. Okay. So the pulse width that you get is all passive. Okay. So it happens naturally. And if you want to, in this type of laser, because this is a nonlinear crystal, in order to get to a faster pulse width, what you'd actually have to do is turn up the pump laser.
Mm-hmm.
Okay, so that's going to create a greater shift in the refractive index and group velocity dispersion in this crystal, and then the change in the refractive index in the crystal and the group velocity dispersion, and then the compensation that's applied by this arm, essentially all work together to compress that pulse into a very small time window,
Okay.
and it does. Again, I know it's a lot, but it does that by lining up the phases of all of the different waves that are in these different modes so that they have a specific phase difference.
Mm-hmm.
And it's by lining up those phases together that then allows you to then that then causes all of the waves to interfere in such a way that you get a very fast pulse.
How do you
So
set
this
up
is
this kind of machine? Uh,
how do you set this up?
yeah,
It's
do you need to
extreme.
like measure it, or
Yeah, so alignment in lasers is a very time-consuming task, and it's something I hated doing. So I'm glad I don't have to do it anymore. But and for some lasers, it's best to just call the company and ask someone to come out if they're local. If they have someone even that will come out, they might come out and do your alignment. They might just send you a guide. When I've had to do it, you essentially have to do it like one element at a time.
mm-hmm.
So like you have to make sure that like this beam is hitting a specific spot on the crystal. Then you have to look at the output beam and very carefully align this like R1 here in two axes, right? Because it's got two rotation axes. So then you have to track, okay, where is that beam going? And then you track it over to the prism, and then you have to align that. So it's like one piece at a time, all the way down this line of stuff, and then all the way back out to the output coupler. Yeah. So I've never done alignment on a titanium sapphire laser. So we had one of these in our lab, and there was another guy who worked exclusively like with titanium sapphire, because they were using this for microscopy. So they were using it for microscope images. But what I was doing was with the YAG laser that I showed earlier. So that one, you had to very carefully make sure that the beam comes out in a straight line and hits this crystal where it can then reflect and go off. And it has to go through a filter. You have to very carefully align that, because if it's just off a little bit, it will filter too much, or it will diverge the beam, and then that
How do
beam
you
goes
kind
off where
of
you don't
do it?
want it.
Like, do you keep constantly measuring the output, and based on this, you know if you aligned it correctly or not, or how do you get the feedback from?
Yeah. So you do have to measure the output in many cases, right? And that's just kind of your check that you got all of the energy that you expect to get going to the output, right? So like you can check, where does my beam output fall off as it's moving through the laser?
Mm-hmm.
Yeah, so you can check that, and you would do that with a meter.
So, like building big laser at home, that's not very realistic.
Well, not when you need a lot of these optics, because like the system I showed earlier, the XPLA system, I think the number on that was like $50,000 or $100,000.
Wow.
Yeah, so those ones are expensive. It's the kind of thing that large companies or universities can
Because I
purchase.
guess they don't really sell many of them, do they?
I've never looked. I've never looked. There's a marketplace for everything, though. I'm sure someone's reselling it. Maybe go try eBay. See if someone's selling an XFlow laser. But
And
the like this stuff with like the laser diodes, you can actually get those to accept enough power that they do become dangerous, and you can do it with commercially available parts.
I think I've seen a video about this. Maybe backyard scientists. They built something.
Yeah, and as I recall, Hacksmith did it. I've seen other videos online with people. I've never seen backyard scientists, but I seem to recall seeing other videos where people have done this with like laser diodes.
Okay, what do we have next?
Okay, so the saturable absorber essentially does the same kind of thing as like the Pockels cell, but it just does it totally passively.
Okay.
So you don't have electronics that are switching this thing. It just happens naturally. Okay. So
So
essentially
it
what's happening.
somehow builds up, and then it releases, or?
Yeah, exactly. Yeah. And it's just saturable absorber materials. They're almost like magnets, right? Magnets have saturation magnetization, right? So, you put enough field into it and it eventually saturates the magnetization that you can create. It's the same kind of idea with a saturable
Okay, so it's
absorber,
blocking, and then
and then it
okay.
stops. Yeah. Yeah, exactly. So that's what this is showing. And that's what's happening here in one of these cavities to create mode locking. So this technique where we're basically lining up all of the modes to then create a very fast pulse, that is called mode locking. And so you're modulating the loss in the cavity. And the easiest way to do that is with this saturable absorber material. Okay, so I'm going to try and be quick with this because this is now what I spent a lot of years doing. This is something called random lasers. So take all this stuff with the cavity and throw it in the garbage because you don't need cavities if you can do random lasers. So random lasers are really fun because essentially what I'm showing in this microscope image, both these microscope images, is a bunch of zinc oxide nanoparticles. So if you know what zinc oxide is, you'll know it's in sunscreen. It is commonly available. You can order you can order you can order batches of it from like Sigma Aldrich or another company for very cheap, $50 or $60 I think for decent size container. And essentially what happens in a random laser is the lasing cavity forms totally randomly. You have no control over what these peaks are. So basically on this sample in the lower left, if I were to take my microscope and move it somewhere else, I was good to move somewhere else, these peaks could totally change. So instead of having these, 1, 2, and almost, a third peak here at about 380, they may be somewhere else. And you may even get just one peak. You may get 10 peaks.
That's
So
why it is called
here,
random, yeah, because you can really control the frequency.
yeah, exactly. You have very little control over the frequency. You just know that it's going to happen in a certain range. So this is our background spectrum you've got the wide background spectrum, and then you've got the peaks that happen on top of it. And
And these
so
peaks are happening, they can be happening from different places of these materials, different peaks.
exactly, that's exactly right.
Okay, and how do
And
you
and
excite this kind of material?
so there's been a lot of research to do it electrically. The easiest way is with another laser. So that's by far the easiest way. But you could do it electrically. People have done it. Oh, hold on. Sorry, let me go back. So what I'm doing in this particular experiment in the top left is to check that it's reproducible. And you can see that the peaks are highly reproducible. So they're not changing from exposure to exposure.
So,
And that was what we got when we, sorry about that, I keep clicking here. So that was what we got when we were using a fast enough laser. So when the pump laser we were using was fast enough, meaning its pulse time, then we were able to get this to be fully reproducible. But if the pulse laser was too slow, then what would happen is different areas of the sample would decay too quickly. So it would decay before you could excite it. And where that decay happens is totally random. You have no control over it. So be totally random from shot to shot.
it was like super interesting. Maybe we still could say something like, so, about our topic, like how to build a laser. So if someone really would like to build it, what should they do?
Okay, so if someone really wants to build their own laser that's practical and you're able to actually, use it for something practical and you want to have fun designing something, I would say get a laser diode and design pulse circuit. Pulse circuits, there are lots of different pulse circuits that you can find online to help guide you. And obviously, laser diodes, they're commercially available. They're a little expensive, but they're not like tens of thousands of dollars or anywhere near that. I think some of them are like, hundreds of dollars. So between like putting together a PCB for your pulse driver and then actually getting the laser diode itself, maybe you spend $500, let's say. So, you go overseas to fabricate your board, assemble it yourself. The components aren't very expensive. The most expensive component is just the laser driver. So that's the one. If you want to build your own laser, I would say go give that a try. And you'll actually find a lot of guides online, and I'm sure a lot of YouTube videos that will show some of the finer points with how to work with laser diodes to build your own laser. So that's what I would say. If anyone's interested in doing that, that's what you got to do.
And that's everything for this video. I would like to say thank you very much to Zach. Thank you, Zach, for finding time to help me to create this video. And I would like to ask you to leave your feedback. Did you find this video interesting? Any ideas for future videos? Let me know in comments. If you like this video, don't forget press like button. If you would like to see my future videos, you know exactly what to do. Subscribe. I would like to thank you very much for watching and see you next time. Bye.